In today's digital world, encryption is what keeps our private messages and many important data safe. But powerful quantum computers in the future could break the classical encryption methods we use today. That's where quantum key distribution, or QKD, comes in. Unlike traditional encryption, QKD uses the laws of quantum physics, not mathematical complexity, to keep information secure. It's not just secure, it's unbreakable in principle. Let's imagine Alice wants to send a secret message to Bob. But before she can encrypt the message, they both need to share a secret key, which is a random sequence of bits. How can they do this without anyone else, like an eavesdropper named Eve, intercepting it? The answer lies in photons, tiny particles of light and their quantum properties. Alice begins by sending Bob a series of photons. Each photon is randomly polarized in one of four directions: horizontal, vertical, or at two diagonal angles. These polarizations represent binary bits either 0 or 1. For each photon, Alice randomly chooses one of two measurement bases: rectilinear or diagonal. Bob, on his end, doesn't know which basis Alice used, so he also randomly chooses a measurement basis for each incoming photon. After the transmission is complete, Alice and Bob communicate over a public, classical channel. They don't reveal the actual bit values, but they do compare the bases they used. Whenever their bases match, they know Bob's measurement is likely to be correct, and they keep that bit. When their bases differ, they discard the bit. What's left is a shared, secret key known only to Alice and Bob. Now let's understand why they keep the bits with the same measurement bases. For example, Alice chooses the rectilinear base for this bit, and she sends it to Bob, and he performs diagonal base measurement on this bit. Here we see that the Bob's measurement output is a combination of bits 0 and 1, which is not exactly the bit sent by Alice. Now, if Bob performs the measurement with the same rectilinear basis used by Alice, then you can see that the output is exactly the same bit sent by Alice. But what if someone tries to eavesdrop? If Eve tries to intercept and measure the photons in transit, quantum physics works against her. Because measuring a quantum particle alters its state, her interference introduces detectable errors. When Alice and Bob check a small portion of their key for errors, any significant disturbance tells them someone is spying, and they simply discard the key and try again. In the end, if no eavesdropping is detected, the final shared key is truly secure. Alice can now encrypt her message with confidence, knowing that only Bob can decrypt it. Quantum key distribution doesn't just make hacking difficult, it makes it fundamentally impossible without being detected. This is the future of secure communication, powered by the strange but powerful rules of the quantum world.